Awesome. So now at least we know what is the DC operating point. So this is fine. Now let's look at how the small signal behavior is going to be. Let me erase this. Remove everything. Yeah. So now I'm interested in finding the small signal gain. Now remember, if this was a properly symmetric circuit, for finding the output, what will be the approach I take? You find the common mode, differential mode portions and do it. But unfortunately, this is not asymmetric. I mean, this is not symmetric. So instead of doing that, let's take the approach of finding short circuit GM and R out. Or I would say, I'll find the current V out. Sorry, I'll find the output voltage V out as the short circuit current times R. Okay, so let's find the short circuit current now. Again, remember when I'm saying short circuit current, this is all small signal calculations. So for small signals, what will happen to the output now? Yeah, I'm going to short circuit it as the name suggests. So small signals, what happens to the current source? So I'll basically remove this. Similarly, if I have the supply VDD, what will happen to small signals? And of course, I forgot to add, I have now, this is, let us say, V1 and V2. Okay, I'm adding two voltages, small signal voltages. So I have just V1 and V2 here. So I'm having small signal excitations V1, V2 on the two sides, and I'm interested to find what is the short circuit current. So now remember, to find the short circuit current, I have to find the currents flowing through the transistors. To find the current flowing through the transistor, what voltage I should determine first now? I mean, the current in a transistor depends on what? VGS. So is my gate voltage known to me? What is unknown? So this voltage Vx is unknown. So let's find that. So again, Vx will have contribution due to both V1, V2. So small signals, it is linear circuit. So what do? Use superposition. So let's find only due to say V1, and then we can extend it. So if I draw the circuit from V1, I'll have V1 here. Okay, this is M1, and at the source I have something. And what is the effective resistance here? It is 1 by Gm because I'm looking into the source of the transistor. And remember, the drain is short. Since the drain is short, I can make a comment that the resistance is 1 by Gm. Right? So which means I can say that this is basically 1 by Gm of transistor M2. Correct? But since both M1 and M2 are identical, I will say it GM1. Doesn't matter. So now tell me what will be Vx. I am applying the input at the gate, taking the output from source. So what configuration does this remind you of? I am taking the input from, applying the input at what terminal? Gate. Where am I tapping the output from? This is common drain. So we just saw in the beginning of the class, in general, if I have a resistance Rs here, what is the output? Yeah, we can do it again, but it's basically Gm times Rs by 1 plus Gm times Rs. Okay, if not, we can quickly compute by finding short circuit Gm and R out, but we'll directly use the result. And here value of Rs is 1 by Gm. So I have to basically find Gm times Rs by 1 plus Gm Rs. So what does it become? Fine. So now which means due to V1, my Vx is going to be half of V1. So this is only half the job. I still have to find the response due to V2. So for that, let me assume this side is short. So once again, if I draw the circuit seen from V2, so sorry, this is V2, so this is M2, and I have something here. What is the effective resistance looking here? The resistance looking into the source of M1, how much will that be? I mean, I can say the resistance looking into the source is 1 by Gm, provided the resistance connected at the drain side must be much smaller than R0. So let's look at what is the resistance connected here. What is the small signal resistance here? I have basically connected the gate and drain. So it is 1 by of which transistor? So now as long as my 1 by Gm of transistor M3 is much smaller than the R0 of the transistor M1, which typically will be fine, I can say the resistance looking here is 1 by Gm1. Okay. I mean, in general, 1 by Gm, the order of 1 by Gm is going to be significantly smaller than the order of R0. That's all. Because in saturation, typically Gm R0 is much greater than 1. Right? So which means my 1 by Gm or R0 will be much greater than 1 by G. Again, I am comparing between two different transistors, but still the inequality holds. So which means now I again have an effective resistance of 1 by Gm. So what will be the Vx now? Half of V2. So what will be the total Vx now? Is it clear? Yeah.
Why they not considering the R0 of M4 in this case?
Okay. I mean, I am only interested in the voltage Vx, right? So basically, this is incrementally short. Correct? I don't have to worry about it. Is that okay? Okay, so let me erase this. So now I know the source voltage, so let's find the currents. So what is the, if I call, let's say this current as I1, this current as I2, what is small signal I1? Okay, I can remember, I am having V1 applied here, V2 applied here. Gate, this side, the left side, the gate voltage is V1, right side it is V2. The source potential we just computed as average of the two voltages. So what is I1 now? I mean, I am looking at the small signal drain current to the transistor M1. What will that be? Huh? What is the small signal drain current in a transistor? Gm1 times. So what does it simplify to? Gm1 by 2 times V1 minus V2. Similarly, what do you think it's? What do you think I2 is? Yeah, it is Gm2. Technically, Gm2 times V2 minus Vx, but I'll say Gm2 same as Gm1. So this becomes, you can compute, minus of Gm1 by 2 times V1 minus V2. So if this current is I1, what can you say about the small signal current through M3? That is also I1. So which means what can you say about the current through M4? Minus I1, I1, 2 times I1. Why? Why? Huh? Yeah, the idea is, once again, look at this is essentially a constant current bias scheme. Some current is flowing. The gate voltage will adjust automatically to make sure the current in the transistor is I1. Now the same gate voltage is fed to an identical transistor, so the current will be same. Is that okay? So this current is also, current through transistor M4 is also I1. Correct? So what is my total short circuit current? Yeah, it's basically I1 minus I2 or 2 times I1. So the current flowing here is difference between I1 I2, and I already know I1 is minus of I2. So what is the short circuit current now? GM1 times V1 minus V2. It's essentially twice of this current. So which means if I were to define a short circuit GM, which is the short circuit current by the differential voltage V1 minus V2, what will this be? GM of which transistor? M1 or M2? Yeah, I can write M1 or M2, doesn't matter. I mean, it should not be surprising because it is the transistor M1, M2 which is actually taking in the voltage and converting it to a current. So it shouldn't be surprising at all that the short circuit GM depends only on those two transistors. What's the doubt? You are saying, I mean, yeah. If let's say M4 is okay, so basically your question is, if this is connected to ground and this is not connected to ground, yeah, then it will be different. The idea is the gate to source voltage must be same. Okay, so now we found the short circuit current or the short circuit GM. What is the second part? R out. So let's do R out. So let me actually take this out. So now I'm trying to find the output resistance. Oops. Let me actually erase all this. Okay, how will I find the output resistance? I'll apply a test voltage source, say somewhere here, and find the test current drawn. Okay. So I can basically find the effective resistance looking down and the resistance looking up. So I'll just try to do it explicitly. So for finding that, as I mentioned, the way to think is the following. Instead of applying 1 voltage at this node, I can assume that this node is split. Basically, I'll assume that I have 1 voltage connected here, Vt, and another voltage Vt connected. Still the same. And I'll try to find what is the current flowing in this branch. I'll call it the down current. I'll find the current here. I'll call it the up current. That's what I have to do. So first let's start with the downside. So I'll try to find the down current first, or let's say I try to find the now I have again I have 2 voltage sources. So linear circuit, what will I do? Superposition. So let's try to find the response only due to the yellow source. So I'll assume this is short. So I'm basically applying a test voltage at the drain, and I'm trying to find the resistance. So what am I effectively computing? I'm finding the effective resistance looking here. Fine. So if I were to draw that part alone looking down, again when I'm computing the test voltage test current business, what will I do to the inputs? Yeah, because I don't want them to contribute to my test current, so I'll actually have to short them. Right. So I'll try to draw the effective setup what I have here. So I am looking into the drain. Gate is incrementally short. M2 is there. And what is the resistance looking here now? Again, we just saw it some time back. It's 1 by GM1 or 1 by GM2, because the drain side is at a lower resistance. We just saw it here. Since the resistance at the drain is much smaller, I can say that the resistance looking into the source is 1 by Gm. So if I were to write it, it's going to look like this. Now I'm trying to find the resistance looking into the drain. What does this configuration remind you of? Cascode. So what is the equivalent resistance I will see? It is essentially the resistance I have here, which is 1 by Gm2 plus R0 of the cascode device, which is R02 plus Gm2 R02 times 1 by Gm2. So this is essentially what? 1 by Gm2 plus 2 R02. And for practical reasons, if I were to approximate this, what will I approximate it to? 2 times R02. Again, remember the order of 1 by Gm is usually much smaller than the order of R0. So I'll basically, yes. Yeah, correct. It's 1 by Gm1, but we assume that the two transistors are identical. So the properties are equal. I mean, unless otherwise it's mentioned, we'll assume that the two halves are equal, identical, right? Great. So now tell me what is the down current I have due to this voltage source. Can you tell me what is the current I will have here due to this voltage source now? Vt by 2R02. So now I found the response due to this yellow voltage source. Again, remember in general, as I mentioned, this voltage can result in currents both the downside as well as in the upside. So let's actually see what happens. So I have this down current here. So this current has to flow here. And then where will it go to? I mean, it's flowing down, but where will it go to? Through which transistor? M1, M3. Sorry, I will not draw it like that. So it goes like this. So which means the current flowing through transistor M3 is also this Vt by R02. Which means what can you say about the up current now? It will also be same. Essentially this transistor is, I mean this voltage source is also contributing to your up current. Is that clear? So I have some current flowing down. Now I have this negative feedback connection. So the gate voltage will get set up automatically to make sure the current is equal to this value. And the same gate voltage is copied to the transistor M4. Okay. So the current flowing here is also going to be the same value, which is Vt by 2R02. Is it clear? So I can write my up current is 2 times R02. Okay. Okay. So I have just found the response due to one voltage source. Now it's time to find the response due to the other voltage source. For that, I'll assume that this is now grounded, and I'll now take the effect of the blue voltage source. Yes.
How you are concluding that the current flowing through M2, M1, M3
Right.
equal to M4?
Okay. So you know that, I mean, you're okay that the same current will flow through M2, right? So what, which means the gate voltage here will be set to a value to make sure that the current in the transistor M3 is equal to this, correct? So which means the same gate voltage is fed here. It's current mirror action, yes.
Sir, but we are using the threshold of NMOS only.
Threshold of NMOS, I didn't understand. Okay, so if this is clear, so then let's move on to the other contribution. So I've already written the contribution due to the yellow voltage source. Now let's try to find what is the contribution due to the blue voltage source. So now I am applying a V-test here at the drain. So what is the current flowing now? I mean, basically I'm trying to find the resistance looking into the drain. What will that be? Yeah, remember what can you say about the gate voltage here? Small signal gate voltage. Can you make any comment about the gate voltage? Why 0? Why? I mean, is it 0 or non-zero? Let's first conclude that. Non-zero. Why non-zero?
Because the current is flowing, it has to be some VGS.
Where is the current flowing?
VT by 2 or not.
Okay, remember that. Okay, if this VT by 2 or not was flowing when I applied the voltage source here, right? Okay, if it's confusing, let's actually separate it out. Okay, I think that is a point of confusion. Let's remove this. So I'll have I up, I down. Okay, so let me write it here. Due to the yellow voltage source, I know that I had the same current flowing here. Okay, so let me erase this. Now I have only applied the blue test voltage source. So now tell me what will happen. Now is this 0 or non-zero? Yeah, why non-zero?
Because we are applying some voltage, so some current will be there.
Okay, current will be there. So
Due to that current, there has to be some VGS.
why? I mean, again, this is essentially the understanding cause and effect, right? So current is flowing, right? But remember, if the VGS has to be set, this difference between the transistor current and whatever current is flowing here has to be fed back to gate or source. Right? Again, it is saying that I go and have food and then do my business in the toilet, not the other way around. So understand what is cause, what is effect. Right? So just because I push in a current through a transistor doesn't mean the gate voltage will automatically get set. Automatically, right? So there needs to be some connection from your sensing port to your controlling port. So which means just because a current is flowing here, can you say the gate voltage will get set? So what is it 0 or non-zero now? 0. Why 0?
Because it is short circuit.
What is short circuit?
We are calculating short circuit.
We are just calculating R out, right? There is no short circuiting here. We can't say right now. So when can you say? Okay, now tell me one thing, right? So let us say there is some current flowing here. Do you think because of this current, some current will flow here? Yes. Why? Why so? Again, understand the cause and effect. What causes what? So just because, again, this is again classic confusion. So just because I push in a current here, do you think the same current will flow here? Why? Explain. Why? Yeah, I mean, remember that as I mentioned, for the gate voltage to be set properly, there needs to be a feedback. Correct? Here you are just pushing in a current. Why will this gate source care? It is floating somewhere. Right? See, unless you have some kind of a mechanism to sense what is the current that you are pushing and what is the current in the transistor, and sense the difference and go and correct gate or source, the VGS is not fixed. Is that clear? Okay, right? I mean, if I turn the switch on, the fan will rotate. But if I rotate the fan, will the switch get turned on?
Yes.
Yes. Oh, not will the switch? No. If you do some feedback, it will. But as of now, if I rotate this fan, will the switch turn on?
Actually, sir, for home, sir, actually.
It's okay, man. That is a feedback. Okay, you're not understanding the joke. You can't make a joke to people like you who keep arguing, huh?
We can comment about VX voltage.
Where is this voltage? Okay, what do you want to comment about that?
V1 plus V2 by 2.
No, there is no V1, V2 here. Why?
That's why V1 and V2 are 0. So
But not necessarily true, because now we added a third excitation as V-test, right? What he was saying is, I knew Vx was roughly V1 plus V2 by 2. Now in my experiment, I made V1, V2 to 0. So can I make this claim? I cannot, because now I have removed this V1, V2. But in addition, I have introduced a third voltage source, right? I mean, V1, V2 0, but I have a new excitation V-test. Maybe that can contribute something here. Not clear it. But at least this is argument correct. Some current is flowing, let us say.
We have already the drain of that M2 is ground.
Drain of M2. Sure, okay.
So
That doesn't mean anything, right? I mean, that's what, let's come to that. So everyone is agreed some current is flowing here, but will that current get copied here? Is that clarified? That's the important point, right? I will rotate the fan, except for this fellow, the switch will not get turned on, okay? So this current is 0. So what can you say about the gate voltage then? No current flows in this transistor. This is 0. So which means if I look at this fellow, I have, if I look at M4 alone, right, I am applying a test voltage here. This is M4. Where is my gate connected to? Small signal gate is ground. So essentially I have a case where gate is small signal ground. Sorry, I'll draw it like this. So what is the resistance looking into the drain now? R0 of which transistor? Is that clear? See, is everyone understanding this part? The small signal gate voltage is 0. Is that clear? So which means if I were to draw M4 alone, this is how it is going to look like. So what I have here is a transistor whose gate and source are shorted. For small signals, how can you model a transistor as? I mean, not just a resistance, right? What is the other thing? Voltage controlled current source. What is the value of the voltage controlled current source? GM times in parallel with. Now what can you say about VGS? So which means what can you say about the current? So what is the effective thing you have now? So what is the resistance looking into the drain? Or not of which transistor? So which means now I'll have up current, which is VT by. Okay. Current through M3. Okay, the point is because I am changing the drain voltage, of course some current is going to flow in the transistor M4. Now the question is, will this current get copied onto M3? That will not, because see, again the question is, just because some current is flowing here, the gate voltage will not change automatically, correct? Only if there is some kind of a feedback from here to here, that will change. So as of now we are pushing some current, but the gate voltage, there is nothing fixing it. So this is going to be 0. There is no excitation that is controlling the gate voltage. See, unless we have some kind of a feedback from here to here, so the gate voltage is 0, so which means this is going to be 0. And again, here both gate and drain are shorted. For this transistor, VGS is 0, VDS is 0, current will be 0, which means this current is also 0. So which means this voltage will also be 0. So which means this voltage is 0. So do we have any contribution due to Vtest to the down current? Right, so this will be 0. Okay, so now I found the total up and down currents. So, so what is my total up resistance now? Here I have the total up current. So from this, can you tell me what is the total up resistance? It's like watching India-Pakistan match throughout night and saying who is Kohli, huh? 2 or not 2? Plus? Is it plus? Is that correct? Oh, okay, again. Correct. It will be, I mean, VT upon I up, correct. I mean, I'm basically trying to find Vtest by I up. So what will that be? Is it clear that this is going to be 2 R02 parallel with R04? Is this clear? No confusion? So what is my down resistance now? 2 times. Hopefully that is trivial. So which means if I let me rewrite things. So my up resistance here, let me change it like this. If I look at the up resistance, how much was it? That was 2 R02 parallel R04. Similarly, the down resistance is 2 times R0. So what is my total output resistance now? It is a parallel combination of up and down. What will that be? R02 in parallel with, is that clear? I have 2 times R02 and 2 times R02 in parallel. That reduces to R02. So effectively the looking in resistance turns out to be parallel combination of R04 and R02, right? But that doesn't mean that looking up I have R0 of M4, looking down I have R0 of M2. So that is something you should always have in mind. In fact, the looking down resistance, it is not R02, it is 2 times R0. But luckily all the stars and planets align in such a way that the total resistance is simplistically R04 in parallel with R02. The total result is fine, but doesn't mean that individually they are R0 and R. Great. So now we have found R out. So I already computed the short circuit current, which was GM1 times V1 minus V2. Right. So what is my total V out now? GM1 times R02 parallel with R04 times. So the small signal gain I have is how much? It's GM1 times R02 parallel with R04. Okay. So now let's take a step back and compare this circuit with our original circuit. But before that, is the calculation clear? The short circuit current and R out. Again, there's a common point of confusion is what you guys had. That's because I push in a current, voltage will not get set except for him. So please understand the actual cause and actual effect. If you want the gate voltage to be set to some value, there needs to be some feedback, or some voltage source must be sitting there and fixing it. If not, gate voltage will be just floating in the air. Okay. Great. So let me just look at our So here this is our circuit. Here we know it is GM1 times the R02 parallel R04. Correct. Now let's compare the earlier circuit we had. So here you see the gain is how much? If I compare these two, which is having a higher gain? Our new 5 transistor OTA has the higher gain, and it's basically double than what we have. Right? Now stare at the circuit and tell me if that makes sense to you. Let me actually copy this. Hold on. Let me clean this up. Let's not worry about this. I'll even replace it with an ideal current source. That's what we did here. Yeah. So biasing also will remove, doesn't matter. So now here it seems like the gain is double than what we had here. Right? Anyone care to explain why this makes sense? Some any starters? What is the difference between these two? Oops, sorry. What is the difference between these two circuits? What is the only difference? This just because I made a connection like this, so seems like I'm getting double the gain. So what is special about this now? Okay, so let's try to calculate the short circuit GM for this fellow. Right? If you try to find the short circuit GM, again, current source is going to be open. So let me open this. So I'm going to short circuit this. So again I'll apply same thing. V1 and V2 will be there, and again by now you should be able to tell me what is Vx. V1 plus V2 by 2. We did it twice already today. So it is V1 plus V2 by 2. So what is the current flowing here? If I call this, let us say I1 and I2. Okay. So the short circuit current depends on what now? No, okay. In terms of I1, I2, can you tell me what is short circuit current? I1 minus I2. Why? I have I2 current here. Where will this current eventually flow to? I mean, I'm trying to find the relation between this short circuit current and these two currents. Okay. So, what will be ISC now in terms of I1 and I2? Okay, I have some current, right? So, okay. So let's say it's, I2 is flowing this way, for example. Where will I2 flow eventually? I mean, okay, what all paths I2 can take? Tell me that. It can go here, or where can it go to? To this. Which path will it prefer? Why? That's a short circuit. So what will happen to I2? I2 will completely flow through short circuit. So what is my ISC in terms of I2? Equal to I2 or something times I2? Fine. And what can you say about I1 and I2? How are they related? I1 equal to? Is this clear? Because remember, for small signals here I have an open circuit. So KCL will tell me I1 plus I2 0. So I1 has to flow like this. Okay. Whereas here if I do the same calculation, let us say I have the same thing, V1, V2. This voltage is going to be again V1 plus V2 by 2. I'll have similar currents I1, I2. But here if I short circuit this, right? Now tell me what will be short circuit current. We actually calculated. So I have definitely I2 will flow through ISC, no doubt. Right? So I'll have as minus I2. But will that be all? Yeah, I have I1 flowing through this transistor. So I have this gate drain feedback that will generate an appropriate gate voltage here. So what can you say about this current? That's how we calculated also, right? So what is my contribution of I1 to short circuit current? That will just add. And you already know I1 is minus I2. So you'll have 2 times I1. Whereas here I have essentially short circuit current is equal to I1. So this is equal to I1. Whereas here I have 2 times I1. I mean, logically it should make sense because see, here I have 2 halves, correct? I am taking the output only from one half. So which means I am sort of wasting the current flowing in the other half. Because this current is just flowing here and not contributing anything to your output. Correct? Whereas in this circuit, I have currents flowing through both the transistors on both halves. I am not wasting the current flowing here. In fact, I am copying the current and mirroring the current and copying it to the output side so that both the currents add up. Right? So that is why you have twice the gain here. So that is why this is actually a much better circuit to use than this one. Because here you basically wasting half of the signal current. Right? You're not utilizing the signal current flowing on this side, whereas here you basically are using it.
So if you take output differentially,
I mean, we have not come differentially yet. All I want to make is this fellow, whatever you used in your lab. I want to take the difference between two voltages, amplify it and provide here. One output, two inputs. Okay. We are focusing on this for now. Okay. Cool. So we'll stop here and we'll continue. Yeah.